Okay, I want to talk about web application performance and scalability. Another one of these engineering concerns. We've done a lot with functionality and different deployment architectures in this course, but realize for web applications, no matter what architecture you choose, you have to deal with, if you have a successful website, potentially thousands, if not hundreds of thousands, if not millions of users from around the world hitting your website. And how do you do that in a scalable fashion? Um, there's a lot of how-to that goes into that. The focus of my talks here are going to be on what performance and scalability actually are, how they're measured, and the different types of software engineering processes and testing that you do around them, as opposed to specific techniques for doing them. The specific techniques that you're going to apply for performance and scalability, I would tell you the best piece of advice I can tell you from my practical experience is you have to know what kind of traffic to expect is hitting your website. And from some of the parts of this talk, there's ways you can even manipulate what parts of your code and what parts of your system get hit more frequently or designed in different ways to handle either increasing load or to maximize response time, the principal performance metric. So, anyway, let me get started by talking through a few definitions and a few terms that maybe you don't normally hear. And again, just like we talked about on the DevOps side, there's kind of an IT aspect to this. Performance and scalability are concerns for production. And again, like we talked about in DevOps, production was always kind of the ops world and concern, and it still kind of is. But we want our developers more involved. So you have to get used to this kind of language that your operations folks will use when talking about the production environment. First is quality of service, or QoS as an acronym. It's defined with respect to a performance measure to indicate an acceptable level of that service. And maybe not just acceptable, but different tiers of acceptable levels of service. You've heard me talk about quality of service with ESBs. We talk about quality of service with, say, our TCP/IP networking protocol and different features that it adds for each level. Like I talk about TCP/IP, for example, because at the TCP level, we are adding qualities of service by including things like checksumming, including things like arranging the packet delivery on the other end and doing that ordering, where that's not guaranteed if we just use the IP level. At a higher order here with quality of service, it is some performance measure. So it could be a response time, it could be downtime, it could be whatever that performance measure is. There's some one or more acceptable levels of that service, and usually you tie that to some kind of money. One of the ways you tie it to dollars, if you will, is through a service level agreement, or SLA. This is a usually contractual guarantee to meet various performance criteria under defined operating constraints. The defined operating constraints give you as a service provider the assumption, and provided the operating constraints are met, then the software, the system, should meet those performance criteria. And it's usually a contractual guarantee. And if your system does not, if your delivered system does not, then usually there's financial penalties that are involved with that. You have to make the situation right, and usually you have to give back money if you can't meet those levels of agreement. And realize quality of service, and particularly SLA, service level agreement, these are things that are defined in all ranges of service. This could be the service your plumber provides, the service the cable company provides to you in your home. It's a contractual agreement for that level of service, and if it's violated on the service provider side, and you as the writer of the software are the service provider, then again there may be a penalty to pay. You can expect that you're going to operate under certain constraints and certain expectations. Like, you shouldn't be financially hit with a penalty if all of a sudden the load is 10 times what you expected, or the servers or cloud-based servers or whatever the infrastructure you're provided to host your software on by the consumer is no longer valid or no longer operating correctly. Resources, low-level terms, service tied to a physical environment, the RAM, the disk, the network, the CPU. When we talk about resources, these are typically, it's implied that we're talking about computational resources. Very often it's CPU, very often it's RAM. To a certain extent, it can be disk or network. It could be any hard resource that an operating system provides. Well, it's kind of redundant. It's the number of socket connections, the number of file handlers you can have open at a time, supported by your operating system. It's something that's going to have a hard hard limit. And when it has a hard limit, there may be contention. In fact, I'm going to skip down to bottleneck, right? A bottleneck is a component that performs the poorest with respect to other components. It could be the slowest. It could consume the most resources. So you could have a bottleneck on your CPU based on some component in the system that's requiring a lot of CPU. Very often in Java-based systems, you worry about memory utilization and the taxing that does on the garbage collector and how often garbage collection happens. You have something that uses up too much memory, the garbage collector will run too frequently and it'll drag down your throughput. Profiling, a process to understand the resources consumed by or quality service of one or more application components. And typically, profiling is a dynamic. It's at runtime environment. You're watching the resources that are consumed. Typically, what we used to do on profiling is we get a profile footprint of each individual component of our system, and then think about when we start putting those components together, whether bottlenecks would arise. So if we have two different components that both use a lot of memory, we kind of would expect when you put them together, you're going to get more than just the additive effect. You're going to start to see some contention there. Benchmark, establishing baselines for comparative analysis. What's a baseline? Well, like a benchmark, establishes a known point in the measurement of the system. All right, so a baseline is typically something you do. You measure internally as a starting point, and then when you make a change to your software, you have this baseline to compare against. All right. Benchmarks are established baselines. By established, we mean very often they're either internal benchmarks, meaning they're recorded on past releases of your software, or they're industry benchmarks published for other products that provide the same service that you're trying to provide. Clustering, the ability to allocate more resources, usually entire servers, but it could be any one of our computational or combination of computational resources, and maintain the interface of a single logical application. So our ability to add more copies of something, all right, not just servers, but more copies even of a software service, but not have to change clients so that they're aware that there's multiple copies. And then finally, elasticity, the ability to expand, contract resource provisioning on demand, scale up, scale down type of thing. And elasticity is a term we commonly hear with the cloud nowadays. So there's a no pun intended, set of definitions. From here, I'm going to go forward next and talk about scalability.